already. I'll get that set up way faster in the future, but we waited just for you.
Thanks.
Not really, but it worked out that way. Chapter 14, we are talking about homomorphisms. And back to your question, it seems like we did something with homomorphisms in analysis. I couldn't remember.
Like once I saw homomorphisms, like that was just
Recognize that term, yeah.
Was that analysis too?
May have been.
I don't recognize it.
oh, okay.
It may have
And I
been.
feel like I would have
analysis.
because typing out homomorphism was really hard for me. I was like, wait, another
There are too
MO?
many M's in it. Way too many. Okay, so what is a homomorphism? If G and H are groups, a homomorphism from G to H is a function such that for any two elements A and B and G, you have f of AB equals f of A, f of B. If there exists a homomorphism from G onto H, we say that H is a homomorphic image of G. Now, what is different from a homomorphism and an isomorphism? Yeah, it doesn't have to be bijective here. You don't have to be one-to-one and onto. It just satisfies the property. Okay? So we have our homomorphic property. Let's look at some examples here. Let P be the set of E for even, O for odds, and we're going to define f that takes the integers to P to be the function f of z equals E if z is even and O if z is odd. We want to show that f is a homomorphism. So I'm just going to copy this. How do we show that it's a homomorphism?
Just show the.
Yeah, we have to get two elements. So what do we want to call our two elements in the integers? Okay, x and y. Let x and y be in the integers. Then we are going to look at the product, and we're going to have cases depending on the product. So the case that we're looking at is x times y is even. Do we know that f of x times y is equal to? Oh, we're getting there. Has to be equal to an even value, right? What you plug in, if it's even, then you get an E out for your answer. Okay. Now, tell me about how do you get x and y even? Yeah, so let's break this up, and we'll say x is even or y is even. I'll break it up into four cases. X is even, and it doesn't matter what y is. Okay? Then f of x, y is equal to an even, but that too. What does it mean when you put f of x times f of y? Yeah, because that's what we're getting ready to do. We have to look at f of x times f of y. Yeah. So how would we do that?
I mean, that's an even times an odd.
Yeah. So in this is going to be, which is equal to an even times anything. So this is going to be f of y, right? But what is an even? I'm going to put times in here. What is an even times anything? It's even, right? Also even. Yeah. Yeah, you think of functions. Yep. So that's f of x times f of y. Because an even times anything is even. Then now f of xy equals f of x times f of y. The second case, y is even. In this case, similar. The e into the f of y. And then the third case is x and y are both odd. What do we get for odd times odd? So when we come down here, you're going to have f of xy is equal to an odd, but that's equal to an odd times an odd. Let me do it this way. Odd times an odd, 0. Odd times an odd, which is equal to f of x. Okay. In all four cases, well, in all three cases,
Two of them are kind of
yeah,
doublets.
double, yeah. In all three cases, we see that f is equal to f of x, f of y. That's sort of taken care of in this case. This is x is even and y is anything. And then down here, this is y is even and x is anything. Because really the even is what changes the parity when you multiply it together. So that gives us our homomorphism. You have to prove that something's a homomorphism if you're going through the same process, except I believe on your homework you don't have cases. Yeah, I believe, as far as I recall, you don't have cases. Yeah. Okay, so let's continue. We have a theorem here. It says let G and H be groups, and F is going to be a homomorphism from G to H. We want to look at F of E. We want to show F of E equals to E, and F of A inverse is equal to F of the value A inverse. So this one was, I believe, proved in the book. I didn't write myself a note whether I was outlining and proving it. This one's proved in the book, so we're outlining the proof for this one. What's the hypothesis? Let G and H be groups and F be a homomorphism. So the first thing you have to do is show that F of E equals to the identity. But remember, this first E is the identity in G, right? And the second E is the identity in H. Remember, they use a trick. The trick that they're going to use is E sub G is equal to E sub G, right? When you multiply the identity times itself, you get the identity back. And apply and when you apply homomorphism, you get F of E sub little g be equal to F of E sub little g, sorry, two of them. You have to take that through, right? And then from that step, all you have to do is apply inverses to get what you need. When you apply the inverse, you're going to have F of E sub G inverse times F of E has to be equal to F of E sub G. But what's that equal to? Yeah. So on the first side, you have the inverse in H has to be equal to f of E sub G. That makes sense?
In the book, they didn't have the subscripts.
No, they didn't. Makes it clearer when you have the subscripts, but you don't have to put them on. So that proves part one. How do you show part two? You're going to just plug it in. Yeah. So you have f of a, because you're trying to take the inverse of this value, so you're just operating on it with this value right there. Apply your homomorphism. So you're going to get, this is f of a inverse a, but what is a inverse a? And that's in G. So then apply part one. To have on this side over here, f of E sub G has to be equal to, oh, it just went away. It's E sub H, right? So you have this first part has to be equal to E sub H. Is equal to the identity, apply the definition of inverses. You're going to have f of a inverse has to be equal to f of, and the inverse goes inside. And now you're done. Yay. So that one isn't a real long proof. Now we have a couple more definitions. It says let H be a subgroup of a group G. H is called a normal subgroup. We should fold that. H is called a normal subgroup of G if H is closed with respect to conjugates. I'm going to put an H in here. I don't like it in anything because what does a pronoun refer to is difficult in some cases. So if H is closed with respect to conjugates, that is, for any A in H and X in G, you have XA, X inverse is in H. We're actually going to do an example where we're going to find the conjugates, so we'll get practice doing that. But that is a normal subgroup. Normal subgroup means you can do XA, X inverse, and it still is in the subgroup H. Now, you guys taken linear algebra? You remember doing the one form P inverse AP or PAP inverse, it depends on which way you want to do it. It puts it in Jordan canonical form. Do you remember putting something in Jordan canonical form? Nope?
No.
Okay. What Jordan canonical form does for you is it takes a matrix. Because you can look at all of these matrices, you want to know when do they have the same motion on the plane? How do you compare these different matrices with each other? And so someone came up with a Jordan canonical form. That form, you could take the matrices and they'll have a specific Jordan canonical form, a set of matrices do. And that tells you that they have the same behavior on the plane. Yeah, essentially they have the same transformations, rotations, translations, whatever, well, I guess it'd be rotations and stretches. As in they'll do the stretches in the same directions. The sizes of the stretches don't necessarily be the same, but the directions of the stretches are going to be the same. And so that is what your canonical form is telling you. Where is your changes happening? That is very similar to this guy right here. So this normal subgroup is actually a group with a very special behavior. It's something that you can sort of compare this subgroup to other subgroups and see what behaviors you're getting preserved. So that's our normal subgroup. Another definition that we're going to have is the kernel. And the kernel is a definition you're actually going to want to memorize and remember from here on out because it's going to haunt us the rest of the semester. If you want to put it that way, it's Halloween. It should be a good word. The kernel, it's nothing more than everything that is mapped to the identity. So the preimage of the identity is what the kernel is. Everything that's mapped to the identity. Okay, so let's look at, find all the normal subgroups of S3. This is actually part of a homework problem D1, not one that I've assigned, but we need an example of finding these normal subgroups. What are they? Well, I spent some time and wrote down all the subgroups first of all, and from here we're going to figure out which ones are normal. These are actually all the possible subgroups that you can get from S3. Now S3 has its multiplication table on 71 and 72 in your book, so you're going to want to reference that. I'm going to want to reference that too, so let's open that up. It's actually multiplication tables on 72, sorry.
Gamma is an inverse.
Yeah, gamma squared is epsilon. Kappa squared is epsilon, and alpha squared is epsilon. Yes. So let's actually just calculate for the first subgroup. So we have to calculate for each element in here, we have to look at, I need to go up one more. We have A is in H, so that would be the elements in our subgroup, and the X's are in our group G. So we have to operate with all the elements in S3, and we have to check each of them. So if I look at, if we start with epsilon in X3, we'd have epsilon, and then we have our first element right here. Really didn't want to do that, but it didn't change anything. Epsilon, and then epsilon inverse. Well, that really didn't do anything. There we go. But if you do epsilon inverse, that's just the same thing as epsilon, right? So if you work on the first two, epsilon working on epsilon just gives you epsilon, and then epsilon inverse is just epsilon, and so that gives you epsilon, which is your identity. So the first one just gives you the identity. And then I'm working epsilon through all three elements in my group. And so then we're going to have epsilon beta, epsilon inverse. But this one actually isn't very fascinating. What is epsilon beta? Beta. And epsilon inverse is epsilon, but that's just beta. And then when I do epsilon alpha, epsilon inverse, epsilon alpha is just alpha, epsilon inverse is epsilon, and that's just equal to alpha. So all of those are in my set. So the first element from X works with everything, first element from the group. Now we're going to do, I'm going to epsilon, and then for instead of epsilon, what's the next one? Alpha. We'll look at alpha in our group of S3. So I'm going to do the same thing. We're going to have alpha, epsilon, alpha inverse.
Anything that ever has epsilon in there is always going to work, right? Because
yes,
it's
because
just gonna
alpha
turn into
epsilon is going to be alpha, and then you have alpha alpha inverse, which is just the identity, which is in your subgroup. But now it gets a little more entertaining. You're going to have alpha, beta, alpha inverse. So what is alpha, beta? Look on your table. Alpha goes on the row and beta comes from the column.
Alpha inverse is just alpha. So
Yeah.
Alpha beta is
gamma,
Alpha, beta is gamma.
and alpha inverse is alpha,
Alpha inverse is alpha. So now tell me, what is gamma alpha?
delta.
Delta. Okay, so is delta in this setup here?
No.
No. So as soon as I get something that isn't in my set, I know it's not a normal subgroup. So that means epsilon, beta, and alpha is not a normal subgroup. Does that make sense?
It has to be.
It has to be back in H. Yeah, it has to, all the conjugates have to live in your original subgroup.
There's 9,
What do you mean 9 total?
there's 9 ways.
There's actually going to be, if you think about it, you have 6 with 3, so yeah, you can have 18. But you don't have to do, if you want to shorten it, you know anything that's already in the subgroup will be back in the subgroup because the subgroup is closed. So you really only have to check those elements that aren't in the subgroup, which would be just 3 elements. So you have 3 times 3, which give you 9. So yeah, you're right. There's really only 9 that you have to check. And you really don't have to check the epsilon because it always works. So there's really only 6 that you have to check. So let's actually check the next one is epsilon gamma. For epsilon gamma, we don't need to choose epsilon or gamma. So let's choose alpha and see what we get. I don't need to do it with epsilon because it's always going to work with epsilon. So let's look at alpha, gamma, alpha inverse. What's alpha gamma? Beta. And then alpha inverse was alpha. And so beta alpha is kappa. Is kappa in our set? Nope. So it's not a normal subgroup. You guys get this process? Okay, so let's do one that is a normal subgroup then. The only normal subgroup is this guy right here, epsilon delta beta.
I think it's the lowest conjugate. Any multiplication of together would not really
That's why the other ones don't work. Yeah. Yeah. I forget which one am I checking? Delta and beta. And so we're going to have alpha, and let's just. So what is alpha delta? I get kappa. Yeah. And alpha inverse was alpha, so what is kappa alpha? Beta. So that one worked. Let's do the alpha delta alpha. Oh, I did delta. Beta. Alpha beta alpha inverse. So it's alpha beta. And alpha inverse is just alpha. So gamma alpha is. So that's back in the set. That one worked. And so now I don't need to choose beta because beta is in my set. It's gonna work because it's a subgroup. So I can skip beta. I can skip delta, so I just have to do gamma and kappa. So now check it. We're going to have, with delta, we're going to have gamma, delta.
We have to do this by exhaustion.
Yep. Unless you have some properties that you know about, which usually we're not going to know about something unless it's a commutative group. If it's commutative, then you can flip the last two and move the inverse next to the original term, make it go away, and you're left with the value in the middle. So commutative is always going to work. Okay, what is gamma delta? Alpha. And gamma inverse? Gamma. For these ones they are, but for the other ones they aren't. So what's alpha gamma? Okay, so that one's in the set. And then we do gamma, beta, gamma inverse. So what's gamma beta?
It's kappa.
Kappa. And gamma inverse was gamma, so kappa gamma is, okay, which is also in the set. Then the last one we have to check with is kappa. So here again, I'm just going to look at, because I have to just check the ones that aren't in my subgroup. If it's in the subgroup, it's going to be closed under the operations. So kappa is not in that list, so I have to do it. And I'm only going to do it with delta and beta because it will always work with the identity. So we're going to have kappa, let's see, delta, kappa inverse. So what's kappa delta? And kappa inverse? Kappa. So gamma kappa,
Beta.
which is in our set. And then we do it with the last one. Beta, kappa inverse. Kappa beta,
Alpha.
and kappa inverse was kappa, so alpha kappa, which is also in our set. Therefore, our subgroup epsilon, delta, beta is a normal subgroup. I really don't want to do that. So do you guys understand how to calculate if a subgroup is a normal subgroup? You do it pretty much by exhaustion unless you know something about some properties about the group. Okay, so that ends up being the only normal subgroup for S3. Now, consider the function f that takes S3 to Z2, and this is going to be given by this property. We're going to take the identity to 0, alpha to 1, beta to 0, gamma to 1, delta to 0, and kappa to 1. Is this a one-to-one function? No, it's not one-to-one. It is onto, it's onto 0, 1. But the definition didn't even say that it had to be onto. But if you want a homomorphic image, it has to be onto. So, it has to be onto for you to say that the image is homomorphic. So if you want to say that two groups are homomorphic, you have to have a function that's onto.
What do you not? If you don't have if it's not onto, what can you have? You can have homomorphism. But not
You can have a homomorphism, but not a
So
homomorphic
this time,
image.
there's actually a difference between, like isomorphism is not that way.
It
right?
isn't that way. For an
Isomorphism
isomorphism,
is
it's
the same.
bijective. It's one-to-one. It's onto.
And being isomorphic is the same as having an isomorphism.
Yes.
It's not the case.
Yeah. A homomorphism is a function. The homomorphic image is an onto, an image that the function maps onto. So here we're going to verify that F is a homomorphism. This is like a homework problem, so we're actually going to go through the steps here. Our hypothesis is F is going to be this function. Let F be given by this function right here. To show it's a homomorphism, you have to take any two elements in the set and find the image, and then show that it's also the product of the images. So we actually have to go two directions. The easiest way to do this is to do what they did in the book for their example where they, I forget what their example was. It was what they started out the section with. They made one in the wrong chapter. They started with the Z6 and transformed it to even to 0 and 1, 2 to Z3. And so what we're going to do before we actually do that is I'm going to put that up here at the top. We're just going to consider so for this one we have 6 values So I need 7 by 7. Okay. And this one's going to be epsilon, then alpha, then beta, then gamma. Where's my gamma? There we go. And then let's see, delta, and then kappa. The same thing down here. I really don't feel like writing this out. I'm going to say, consider the table on page 72. Because that's what it is.
This is the same thing.
Three that we're dealing with. And the math, looking at Z2. So let's look at the mapping of that. So epsilon goes to 0. Alpha is going to 1. This goes to 0. That goes to 1. That goes to 0. And that last one goes to 1, according to the mapping there. So then that would, then this is 1, 0, 1, 0, 1. Now, filling out the table, so let me put my table lines right here. Looking at the table here, tell me, what does epsilon go to if you're looking on page 71 at that? Yeah, it goes to epsilon. And so you're just going to have that,
They all feel
which is going to be 0. And then this one is going to just go to alpha, which is 1. And this one goes to, do I need to do that or do we get the process? We get the process. Okay, so then this is going to go to 0, 1, 0, and 1. And the same thing that's going to come down here, you're going to get 1, 0, 1, 0, 1. Now here, it's a little bit different. So what would you have in the second row, second column spot in the table on page 71? Is that epsilon? Yeah, on page 71. Yeah, we have to verify that they're the same. So this I'm going to put epsilon and then note that that goes to 0. What would be the third part over here? That's a gamma, right? But gamma is mapped to 1. And over here, the fourth one was beta, which is 0, right? And kappa is 1. And delta is equal to 0. Okay? And then look at the second row. You're going to have a second column is going to be a kappa. Kappa goes to 1. And then this one was a delta, which went to 0. And then alpha, which went to 1. That's 1. And then gamma goes to 1, right? So you guys see how to fill out the table. And to be able to verify then that you have a homomorphism, I'm going to put here and finish filling out the table. You guys can do it. Notice that what you have for the answers here, they work because 1 plus 1 gives you 0. 1 plus 0 gives you 1. So these outside row and column numbers are matching the answers from inside the table. So we know that this table is working, is preserving the properties. So we're just going to say by inspection, above. This allows you not to have to type so much. We see that f of I, that didn't work, has to be equal to f of x, f of y. Because the f of x, y's are the zeros and ones, and the x's and y's are the alphas and betas and stuff like that. And you could have them on the sides too, so you could verify that it actually is working. You have the same table, just translated using zeros and ones from here. So it is a homomorphism because it lets you pass through that inspection. Do you guys see what I'm trying to say? How you can inspect that?
How is that? It wouldn't be a homomorphic image then. It's not on.
It is
It's
on
on
two.
to Z2.
It's on to Z2.
It's not
We're mapping on to Z2.
It's not one to one though.
It isn't one-to-one, so it's not isomorphic.
Doesn't onto mean that you have a full number of.
No.
No, it means you cover the whole image.
You cover the whole image, but you have extra things going to the same. Mhm.
It just means it's
Yeah.
being mapped to,
Yeah.
that's all.
Like
Mhm.
the reels onto one is natural, so it's on.
Mhm. Or like the reals onto the positive reals with x squared.
It's possible to be one-to-one and not one-to-one.
Yeah, x squared. Oh,
Yeah.
sorry, one-to-one and not onto. I thought you said onto and not one-to-one. One-to-one and not onto. Sure.
You
You can.
don't cover the whole target.
Yeah, f of x equals to x when x is an integer is one-to-one, but it's not onto all the reals.
All the real.
So you map integers to integers, but you don't map it to all the reals. So it is one-to-one, but not onto.
There's no function that exists that's like, it's just a function with no,
Yeah.
You don't have properties. Like if you had a set of numbers 1, 2, 3, and a set of numbers, you could define a function that would only map, that would be either onto or.
no, I'm saying, is there a function of, we could say x squared? Is onto, but not one-to-one.
X squared isn't 1 to 1.
Yeah, that's what I'm saying, it's onto, but not one-to-one.
Right.
But is there a function that's just like, this function?
Yeah, you can construct such functions. Mhm. Nothing special about it. So
Wouldn't it just be. That makes sense though.
now something that's one-to-one but not onto.
Yeah.
You just have a bigger set that you're mapping into.
Yeah.
Yeah.
Doesn't that mean that?
Like natural to reals.
Uh-huh.
Okay. I was thinking that you'd still have to have at least one thing that's something you just have.
One-to-one's the same, but there's no.
Yeah, so something doesn't have a pre-image on it. It's fine. So Z2 is a homomorphic image of S3.
So technically, if you were in a complex from graph
Whoa, 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 whoa. The x squared parabola in the complex plane?
have zeros.
Yeah, but you're still taking +1 and -1 to the same y value. So -1 plus 0i and 1 plus 0i. So yeah, it still doesn't work. Uh-huh. Okay, so now it says find the kernel, and then list the cosets of the kernel. Okay, so let's come down here. This is outside our proof now.
It's epsilon beta delta.
Yeah. How'd you tell that?
Given the maps given.
Yeah, you're just reading the map. Whatever had a 0 for an answer. Yeah, really easy. That one, we really like that. Now for the hard one, cosets of the kernel.
They have to have the same.
So remember, yeah, they're going to have the same length, but we have to just calculate them. So the k epsilon isn't going to change anything. That's just going to be k, right? Mm-hmm.
Okay, alpha one.
Yeah, so let's put this right here. This is equal to epsilon, beta, epsilon, and then delta epsilon, which is just epsilon, beta, and delta, which is k. Now, look at k alpha.
You want to simplify those?
We just know it's equal to k, so I just wrote it. So this is going to be epsilon alpha beta alpha and delta alpha. So what is epsilon alpha? Alpha. What is beta alpha?
Delta,
And what is delta alpha?
gamma,
I'm believing you. You better be right. Okay? And then the next one we check would be with beta. But remember,
We just read it.
if you put beta, epsilon beta is beta. Beta beta is what? Epsilon. And delta beta?
Beta, well, beta.
Okay.
Beta epsilon, beta delta, or epsilon beta.
Okay, so it's beta, beta, and
Delta.
yeah, delta, beta. There we go.
so we have a beta,
Beta, delta,
delta,
yeah.
epsilon.
Yeah,
Which
so
is
beta, delta, epsilon, which is equal to k. What it turns out is a kernel is going to be a subgroup, but we don't know that yet, so we have to check it. So then that's beta, and then after beta we get gamma. So we're going to have epsilon gamma, beta, oh wait, is it beta? Yeah. Gamma, and then delta gamma. So I got the easy one. Epsilon gamma is gamma.
Alpha.
Is that alpha? And then kappa. But that's, notice the same thing that we had right there. So that's equal to k alpha. Yes, this is identical to homework problem just done.
It's haven't said that it's a kernel.
Yeah, we haven't said it's a subgroup yet. Yeah. So this is epsilon delta, beta delta, and delta delta. But what does that equal to? Epsilon delta is delta, beta delta, epsilon, and then delta delta. Okay, so then that's just equal to k, right? And then the last one, k kappa. We need one more, right? So then beta kappa, and then delta kappa. Do what? Oh, there we go. This one is just kappa, and beta kappa is, and then delta kappa, which is our same thing as k alpha. So the cosets are just k and k alpha. For the distinct cosets, some of them overlap. Okay, you have a homework problem similar to that. Can we do that? Please say yes. Very good. The kernel of F is a normal subgroup of G, and the range of F is a subgroup of H. This is the last theorem in chapter 14. So, had we known this before the last example, we wouldn't have had to check everything because we would have known anything in the kernel would have made a subgroup. So, this one is proved in the book too, so let's just outline the proof. So F takes G to H as a homomorphism. And how do they prove the first one?
Is that capital S is good enough?
Yeah, that's not supposed to be capital. There we go. Yeah, there we go.
So, if it's a homomorphism,
So what is a kernel? Yeah,
zero.
K is going to be the set of all X such that F of X is equal to the identity, right? And this is going to be the identity in H. Well, we don't know if that's zero or not. Yeah, the X's are from G. Let's put that back.
No, this isn't based on the previous.
Yeah, this isn't based on the previous stuff. This is for an arbitrary group. We want to show it's a normal subgroup of H. Remember, normal subgroup, you have to do X, A, X inverse, where A is in K. So we're going to let A be in the kernel and X in G. Now we just have to look at X, A, X inverse, and we want to show that that is an element of K. I'll put it right here. Okay, that shows the normal part. How would you show the group part?
Right, how do you know that is true?
If you want to show a normal group, then XA, X inverse has to be in the subgroup that you started with.
You don't have to show that, you know, say.
Yeah, it says then show that. We have to show that. To show it's a group, how do you show it's a group?
Go to inverse of
Subgroup, yeah. With respect to so the things that they have to go through and do, they do the first one. How would you show the subgroup? We'll start with that. Close with respect to the operation. So get any two elements in K. I don't know, A and B. Okay, so let's say C. How's that? C and B. Then you have to operate them on each other, right? So you're looking at CB. Now, what do you know about CB?
F of CB, or F of CB is equal to F of C, F of B.
Yeah. Put that up here.
wait, what? F of C is C?
F of CB
It's a
is equal to
homomorphism.
F of C times F of B.
Yes, yeah.
That's equal to F of C.
Sorry, I thought you were implying that C was equal to F of C.
No,
Not necessarily.
And F of C, I know is equal to what?
Epsilon.
It's the identity because it came out of our set K. So this is going to be the epsilon identity in H. Yeah. But what is that equal to when you multiply them together? It's just identity. Conclude, right?
So,
B is in, and close it with operation. Inverses. So we just need one element in there. So I don't know, W, B, and K. Then what do you know about W?
can you go back to that other thing?
Yeah. F of W, W inverse is equal to. But what do we know about F of W inverse?
Can we do like?
Yes, well, W.
Close.
Well, if F of W gives you the
Yep.
inverse of the element, the identity element,
Can we use the one?
the other has to be.
Yeah. So you're going to have the identity element has to be equal to. Right? From operating and use inverses on this equation, so you're doing inverse to both sides of that right there. That is, well, let me simplify it in a minute because that type just going to look funny. That's going to be equal to with, I wanted the W inverse outside for the moment. We'll substitute it in just a minute. Try not to skip too many steps because we can't lose Kristen. So the identity and W inverse. But then that part right there, what does that tell you? Sub H is equal to F of W inverse. But what do you know F of W inverse is equal to? Mm-hmm. I'm right there. So you know, what does that tell you? Yeah. And K is close to inverses. Okay, so that tells you that K is a subgroup. Yeah, now you have to show normal. We're going to have XAX inverse. I want to show that this is in K, so I need to operate on it by F, right? Yeah, we know homomorphism.
Is in the kernel, so that's gonna go A. F of A is the inverse.
Yeah.
Or is the F.
Yeah, I'm going to do that in one more step. So you get F of X, F of A, F of X.
Where is
Inverse.
X live? X lives in G.
X lives in G. But, so then that's equal to F of X, E sub H, and then F of X inverse is the same thing as F of X inverse from our previous theorem. But, so then that's F of X inverse, which is equal to what? What's your conclusion? Thus XAX, yep. And it's in K. And conclude that I cannot spell today. Yep, and we are done. Let me save that before I lose it. Last week I had trouble. I either couldn't save this. Stop that.
So,
So what? Yeah, I think I did. Looks like Thomas joined us. Very good. Okay, and I will actually post this on eClass so that you guys can have the link to YouTube, but it'll be a YouTube video posted on eClass. I'll just post that link on eClass.
We're gonna start our own open courseware for.
As,
Yeah.
as far as the schedule for class period next time, we have a class project after break, but I think we're going to move the class project to before break so we don't have homework over break. You guys tend to do the outlines right before class starts, which keeps it more current in your mind, and I like that idea. So we're going to move class project before break, no outline due next class period. Come to class ready to do a class project, which may just be making sure you finish the homework before you leave. Some form of extra credit. You'll want to be here to get it.
So when you don't know what the project is yet.
No, I just had this inspiration this morning.
Okay.
Don't know what the class project's going to be yet.
Oh, yeah, no homework over break.
Yay, yes.
Well, kind of.
Kind of no homework over break, yes.
So we do have there's no homework, there's now.
Yeah, but most of you guys do the
Yeah,
outline
work
like
session. Yeah.
Tuesday when you get back.
I think mine Monday night.
This is an outline over break. Oh, yeah. The outline.
Yeah, but just do it after break when you get back on Monday night, like you normally do.
I used to do it.
Oh, you usually do it on Sunday? So then you can do it before break. Okay, let's see.
I used to do that, like in history. I would do all of my outlines.
Yeah, because you didn't have time to it.
No, I didn't.
No, those are like 150 pages long.
Yeah.
You said tomorrow what time are you free?
I'm in my office from 11 to 12, 1 to 2, and I'm back in my office at 3:30 for what?
Thank you.
Okay,
Probably 3:30 is when my office is empty.
yeah, that would probably. You said that's what it's supposed to use?
Least use.
Okay, I'm pretty sure I can do that. Cause I have class from 11 to 1 to 2.
Well, show up at 11. We'll see what we can get done. Unless you want to go get lunch at 11.
I usually get lunch at 11 too.
So go get lunch, come back at 3:30.
My 1 o'clock class is fitness and now I'm going to digest before I go.
You don't want to throw up in fitness?
Right. 3:30, that should be good.
Okay, we'll see you at 3:30 tomorrow then.
Are you moving into your
I'm
office?
right now at that. Oh, I'm sorry.
I have a meeting that starts at 3:30 that I'm going to.
That's
Oh,
it.
So the answer is no, I'm not going to be in my office. Yeah, I
Okay.
found out about the meeting at like 8 o'clock last night.
That's
So-
it, Mac impressive.
No, it's university-wide. We either had to go to one this morning at 10:30, which I couldn't go to, or this afternoon at 3:30, which in theory I can go to because it's not listed office hours. But I know many of you work on the homework at that point, so we may end up just doing the homework in class on Thursday. Because the homework that you're
This is
working on,
this done at tonight.
the one that's due tonight, I can still give you an extension on that until, if you want to work on that. What are you stuck on that?
Well, just two issues I was having. One was just one of the examples of coset for infinite groups. H is the line minus X
Mhm.
R. Like, what's the operation? Because like for the other one,
Addition.
it's addition.
So
Add them together.
H is going to be, you can write it this way, X comma X. X is in the reals.
Yeah.
And then you do H of some point AB. That's going to be X plus A, X plus B. And literally, that's how you're going to write it. There's really no other way to do it. You can't do any more than that. And that's for all AB and R plus R.
Okay.
Okay, that makes sense?
Yeah. How do I know like if they're saying addition or multiplication or
When you're dealing with the reals, R plus R, it's addition.
addition?
Pretty much you have to know what you're dealing with to know for sure.
You know, my parents influence.
I've heard it's good, but
It's about like their financial plan for the next 8 years
well, it's kind of important to be
because of
part of.
the student debt is getting ridiculous.
Mm-hmm.
Like there's over $1 trillion in student loan debt, and it's actually more than credit card debt right now.
Yeah,
And so that to like decrease costs, they're going to do this, and they're going to have to like increase our student to teacher ratio from 1 to 14 to 1 to 18 or something like that. And that'll save us money, and then just trying to get like
I think my understanding is also that they're talking about cutting gen ed a little bit, but I don't know if Gordon's going to talk about that today or not.
yeah. My dad's like in the PE department. He's thinking that getting gen ed is going to like one
Your
of the
dad's
first
in the
things.
PE department?
Well, he's over the wellness center. He's
Oh, yeah.
so he's
yeah.
kind of like involved with their like, often that they're thinking that if they cut back gen ed, one of the first things to be cut back is going to be the 50-year requirement.
Can't. QEP requires us to have it.
It does.
Yes. That's part of that. That's a 5-year plan with the idea that it has to go for a minimum of 10 years.
So that one.
That will not be cut.
Probably
Cannot
gonna
be
be history and science,
My guess is it's probably going to come from,
science, because that's what usually is.
probably a little bit from English, a little bit from sciences. Because right now you have to take Com 1, Com 2, and speech, and there's absolutely no reason someone couldn't take speech in high school. No, but a lot of schools are going that direction.
Good.
Mhm. We're giving college credit for that class and for Com 1, but not Com 2. So it might go to remedial and Com 1 becomes a remedial course and not everybody has to take it. I don't know. But I mean, they're going to have to do something. And maybe, history might, I think we have to have 2 histories. One has to be taken on campus. And so that might be dropped to 1 history and you may not have to take it on campus because some people get history credit from high school too, if you take a test for it. Okay. Let me make sure my link is working.
So you're saying alpha is
Who's the one where the
both sides, and then epsilon's
epsilon where they just,
publications.
yeah, it's the side that you're looking at.
Before being the shape maps to the permutation. Before the shape. That's two permutation.
It's this epsilon alpha,
Yeah.
that's what it was.
Yeah, there's everything. And there's your-
Table for before, that's two.
Yeah.